Okay. So the first thing, most important thing to keep in mind is Wednesday is exam 2. And the topics for the exam, remember that all of these exams, all the quizzes, all the exams are cumulative. So you should be ready for stuff before the most recent stuff. So you should go back and refresh your memory all the way back to the beginning. But the topics for this are everything up through free body diagrams. Oh, thank you. Yes, it is. I did plug it in. I just didn't look. What's going on here? Turn on the projector. Here we go. Thank you. So up through free body diagrams. And so that is the assignment that you worked on from Wednesday. I'll do a couple more examples of just free body diagram problems. But then we're not going to have any problems on this exam using Newton's second law. Okay, so no Newton's second law. We'll get into Newton's second law today, and all of the Newton's second law problems are still helpful for getting ready for this exam because they all start with free body diagrams. But anybody have any questions about the test? I will give you all the equations you need. If you ever think you need an equation and I didn't give it to you, just come ask me. Maybe I just forgot to put it up there, but almost in any circumstance, I'd be happy to write it up on the board. Okay, yes?
Are there any questions where it's like A, B, C, D, E? How do I stack with that?
Yeah, probably. Yeah. And I think I mentioned this before, but my usual goal in writing a test, this is an 80-minute class. I try to write the exam so most people will be done in about 60 minutes to give you just, some wiggle room so you don't feel like you're racing. That's kind of what I'm thinking about as I'm writing it. Usually it'll be between 4 and 6 questions, depending on how involved the questions are. Okay, and then the next thing is lab exam 2. Is postponed 1 week. It says in the syllabus that it's scheduled for a week from today and a week from Wednesday, but it's going to be 1 week after that. So I guess that would be Monday, April 7th, or Wednesday, April 8th. Okay. So we have a review lab this week. And then next week, I'm going to be here Wednesday, but I'm not going to be here Monday. There is going to be a substitute instructor in class on Monday. And there is going to be the same substitute instructor is going to be in lab on Monday. That's just going to be, they're just going to have problems for you to work on together. And in the lab, it's just if you need to make up a lab, if you didn't get credit for a lab, You can go to that and make it up. I'll have like videos available. The thing is, it's not going to be somebody who specifically knows this material, So no attendance is going to be taken, but it's a chance to make up a lab if you missed one. And it's also just a chance to work on problems with people. Okay? Yes? So Wednesday will also be a makeup lab, but we'll have regular class on Wednesday. So next week, so there'll be a substitute instructor Monday. The thing is, I'm just planning on being so sick that day. I don't think I can make it in. I'm just kidding. No, I'll be out of town. So the substitute instructor Monday, that's going to be problems to work on in class. I mean, I really do think it would be helpful for anybody who shows up. And then it's a makeup lab. But if you don't show up at either of those, it doesn't hurt anything. Okay? Any questions about either of the two tests or what's going on Monday next week? Yes?
Was the second lab exam have like old stuff too?
Yes. Yep. And yeah, so if you have any questions, well, one thing is, next week, I'm not going to be here for the lab on Monday, but I will be in the lab room on Wednesday. So if you want to just stop by, you don't have to stay the whole time, but if you want to just stop by and go over some questions you have about the lab exam I just handed back, or questions about new stuff we've been doing in lab, I'd be happy to talk about anything. I'd be happy to answer questions about problems, anything like that. You can think of next Wednesday as just like a study hall or like extra office hours or something. Okay. Any other questions? Okay. What about homework questions? Anybody have any homework problems you want me to go over? I was planning to do a couple of examples of free body diagram questions. So going back to free body diagrams, we've already talked about all this stuff. But what I want you to remember is all of the forces that you'll have to deal with in this class are in this short list. So this is all the force types that you're responsible for. First, there's the weight force. And that's always just a magnitude of the mass times 9.81 meters per second squared acting down. And then besides the weight force, every force is produced by contact between the surroundings and the boundary of the object. So these are contact forces. And there are only 3 of these. The first one is pushing contact. Bless you. The second one, and for pushing contact, remember that is parallel to the surface toward the chosen body.
Do you mean perpendicular to the surface?
I do mean that. Thank you. Thank you. That was a test. So, yeah, so like if you have a pushing contact from the ground, that force is always going to be perpendicular to the ground, like coming out of the ground. The second one is a pulling contact. And that involves cables. Or even if it doesn't involve cables, you can treat it like it does. And the rule for the pulling contact, this is the one that's parallel to the cable, away from the chosen body. And then the third contact force is friction. And the friction force always has a magnitude that's equal to the coefficient of friction times the normal force. And it's always opposite the direction of the velocity. Or opposite the direction of motion, in other words. Okay, well, let's just go through a few examples of these. So for the first one, let's say we have two objects, two rolling carts in contact with each other. So this one's 3 kilograms, this one's 5 kilograms. And let's say there's a 20 Newton force here and a 50 Newton force here. And we want to draw a free body diagram of each of these carts. Okay, well, I'm going to start with a 3 kilogram. And so the way you want to go here is draw a closed outline of the body. Then put in the weight force. The weight force always acts straight down. And the magnitude of this is the mass times 9.81 meters per second squared. So if we're in SI units, like we pretty much are in every problem in this class, it's 3 times 9.81, so 29.43. And now we're going to go around the boundary looking for where the surroundings contact the boundary. That 50 over there does not touch the boundary of this body, so that doesn't go in there. The 20 does, though, so I'll put the 20 in. If I keep going around counterclockwise from the 20, the next one I get to is the wheels. The ground's in contact with the wheels. That's a pushing force. And so that force is perpendicular to the ground toward the chosen body. And then just give it a variable name. I'll call this N3. But that's just like writing X or Y or J or whatever. It's just a variable. And then finally, I get to the right side, and the 5 kilogram cart pushes on the boundary there. So the rules for a pushing contact are perpendicular to the surface, toward the chosen body. And I'll give that a variable name, and R is a pretty common one to use for reaction force. Anybody have any questions about that one?
How do you know when to use reaction or tension?
Tension we only use for pulling forces, because that's like the force that the cable is providing. But if you put a T there, there's nothing wrong about that. That's just a variable name. It's just people don't tend to use it for pushing. Any other questions? Okay, and then free body diagram of the 5 kilogram. We have a weight force down, so that's 5 times 9.81, or 49.05. And then over on the left side, the surface is in, the boundary is in contact with the 3 kilogram. That's a pushing force. So that force is perpendicular to the surface toward the chosen body. And since that's the same contact between two bodies as this R over here, we give it the same name R. Okay, so notice that's an important thing to get right. When you have two forces, two objects pushing on each other, the force on body A by body B and the force on body B by body A have to be represented by the same variable. It has to have the same magnitude. Okay? Then we get to the ground in contact with the wheels. That's a pushing force. So it's perpendicular to the surface, toward the chosen body, and I'll give that the variable name N5. And then last, the 50 Newton force is applied to the right side, going this way. So like that. What? The 50? No, we already know that that's 50, so we only put the variables in if we don't know the value of the force. Okay. Any other questions? So anytime you put a variable in, it means that you're going to use equations to calculate what that variable is. Okay. Let's do another one. So let's say on this one, we have two objects that are connected by a cable, and the cable goes over the pulley. One of these objects is a box that has friction. And this one has a mass of 5 kilograms. And then the other one is a cart with no friction. So whenever I draw those wheels on a cart like that, it means that we're not going to be worrying about friction. And let's say this one has a mass of 7 kilograms. And let's say that over here, the coefficient of friction between the incline and the block is, let's say it's 0.1. And then we have to know, whenever there's friction, we have to know the direction of motion of the object, because the friction always acts in the opposite direction of the motion. So let's say that at this instant, the 5 kilogram is going this way, which means the 7 kilogram has to be going this way. So those red arrows are the direction of the motion. So the friction, so what this says is the friction is going to be going that way. Yeah, right. I get confused when people like give me directions, but you're like facing the opposite way at me, like it's more than my brain can process. Okay, so I'm going to start out with the 5 kilogram just because it's on the left and I'm used to starting over there. So free body diagram of the 5 kilogram. Okay, so first of all, gravity always applies a force that's straight down, and that doesn't matter, you know, even though this ramp is at an angle, that weight force is always straight down. So I'm going to draw the weight force like this. And that's equal to 5 times 9.81, so 49.05 newtons. And now I get to, so now I'm going to go around and look for contact with the boundary. At the ramp, with any friction, there's always a pair of forces going on. There's always the pushing force, the normal force, and then there's the corresponding friction force. So I'm going to draw the pushing force perpendicular to the surface toward the chosen body, like that. I'll call that N5. Then there's also the friction force. The friction force is in the exact opposite direction of the motion, or the velocity vector. The velocity vector in this case is like up the ramp and to the right. So that means the friction force has to be down and to the left. And the magnitude of that is the coefficient times this pushing force N5. Okay? And then the last contact with the boundary is the cable. So that force is parallel to the cable, away from the body, and I'll name that T. Any questions about that one? So if I had given this problem and said that at this instant this was going down and to the left and this one was going up and to the left, the only difference in the free body diagram would be that this friction force would be going the opposite direction, because friction is always acting to try to slow things down. Okay? So now I'll go to the 7 kilogram. Let me just make the angle look a little more like my other picture. Okay, so there's a weight force that's straight down, and that's equal to 7 times 9.81, so 68.67. And then there's a pushing force on the wheels from the ground. So that's perpendicular to the ramp toward the chosen body. And I have to give that a different variable name than this one, so I'll call this one N7. And then if you keep going around the boundary, the last contact is the cable. So that force is parallel to the cable, away from the body. And since it's the same cable as over in the first picture, we have to give it the same variable name, so that's T. Any questions about that? Okay, so the next step is we're going to take these free body diagrams and use them in Newton's second law so we can calculate forces, accelerations, stuff like that. So what I'm getting into now is not going to be on the test on Wednesday. But these are the steps for using Newton's second law. So the first step is to draw a free body diagram. The second step is figure out whether the object can move along the x-axis or the y-axis. In this class, objects are always going to just move in one given direction. So determine whether the object is free to move along the x-axis or the y-axis. Okay, if the object is free to move along the x-axis, then our acceleration vector is going to be a0. If it's free to move along the y-axis, our acceleration vector is going to be 0a. Okay, and you don't have to figure out whether the thing is going to move in the positive or negative x-axis or the positive or negative y-axis. Just making the distinction between x and y is all you have to do. The rest, the math will do for you. Okay. And then the third step is, well, now that we have all the forces represented in the free body diagram, and we've figured out how we're going to represent the acceleration, then all we have left is to plug that stuff into Newton's second law. And solve for the variables we're asked for. Okay, so let's do some examples. So for the first one, let's say we have a rolling cart. And let's say there's, well, let's give it a mass. Let's say the mass is 10 kilograms. And there's a force pulling it this way of 20 newtons. And a force pulling it this way of 25 newtons. And we want to calculate first the acceleration vector. And then second, we want to calculate the force vector on the wheels by the ground. Okay, so no matter what it asks for, the first two steps are the same. So we're going to start with a free body diagram. I'll draw the closed outline. And then there's a weight force acting straight down that's equal to 10 times 9.81. So that's 98.1 newtons. And then now we're going to look for contact with the boundary. That 20 Newton force is acting this way. At the wheels, the ground is pushing up on the wheels. So perpendicular to the surface toward the chosen body. And I'll call that N. And then on the right side, there's a force this way of 25. Yeah, sure, that'd be fine. You know, if you put the 10, I mean, that's just giving it a different variable name, so that's perfectly fine. I just did N because there aren't any other bodies in this. And now we have to think about what direction it moves. Is this thing free to move along the x-axis or the y-axis? X, yep, it's just going to roll horizontally. It moves along the x-axis. So the acceleration vector we're going to write as A0. And now I'll go to Newton's second law. So for Newton's second law, each one of the forces in the free body diagram we have to put as a vector. So this 20 is in the negative x direction. So I'll put in negative 20, 0. Everyone with me on why those are the components of that force? Then there's the weight force in the negative y direction. So that's 0, negative 98.1. The force N is in the positive y direction, so that's 0, N. The 25 is in the positive x direction, so that's positive 25, 0. And all of that is equal to the mass of the object, 10, times the acceleration vector that we established, A0. Okay, and now it's just a matter of solving this, this vector equation gives us two separate equations, an x equation and a y equation, and we can use those to solve for variables. So this problem, we're looking for the acceleration vector. Well, the acceleration vector is just this. We just have to figure out what that A value is. And for part B, we're trying to figure out the force vector on the wheels by the ground. Well, that's just this. We just have to figure out what that N is. Okay, so for part A, I'm going to use the x equation. And the x equation says negative 20 plus 0 plus 0 plus 25 is equal to 10a. So add those all up and you get that 5 is equal to 10a. So a is equal to positive 0.5, and that's units of meters per second squared. Well, now that we know the value of a, we can plug it back into the vector that we're looking for. And so that acceleration vector is 0.50. You can also represent vectors by giving a magnitude and a direction. So another way to write this vector would be, well, we know it's in the positive x direction because we have a positive x component. So it's this way, and the magnitude is 0.5. Now we're looking for that blue vector for part B. So that's the y equation. And that says 0 minus 98.1 plus n plus 0 is equal to 10 times 0. So negative 98.1 plus n is equal to 0. So n is equal to 98.1. And so the force vector, I'll call it just force from the ground. Plug this value for n back into that blue vector, and you get 0, positive 98.1. Or if you want to visualize that direction, that's the positive y direction, so it's this way with a magnitude of 98.1. Anybody have any questions about that one? Yes?
It's not about this, but if I still have a question, should I ask him and I want to?
Oh, either one's fine. Yeah. Okay, let's do another one. So let's, this time, let's say we have a body that's hanging from the ceiling by a cable. And let's say that the mass of the body is 20 kilograms. And we want to know what's the force applied to the mass by the cable. Okay, so for this one, the free body diagram has a weight force. So straight down, and that's equal to 20 times 9.81. So that's 196.2. And then there's a pulling force from the cable. That's parallel to the cable away from the body. So this way. And now we have to think about the motion. This is just hanging there. It's not moving. So the velocity is staying constant. What do we know about the acceleration if the velocity is constant?
0.
Yeah, so in this case, the acceleration is just 0. And now we can go to Newton's second law. And so this time what we're going to get is the sum of these two forces is equal to the mass times the 0 vector. The weight force is in the negative y direction, so 0, negative 196.2. The cable force is in the positive y direction, so that's 0t. And those add up to the mass times the acceleration vector, which is 0, 0. The x equation here says 0 plus 0 is equal to 20 times 0. In other words, 0 equals 0. So that doesn't help anything. That just all kind of disappears. But the y equation will give us something. It says negative 196.2 plus t is equal to 20 times 0. So negative 196.2 plus t is equal to 0. And so t is equal to positive 196.2. And this is in newtons. And now what we're looking for is the force vector that the cable applies to the mass. Well, that's this. Oops, hold on a second. So we're looking for this vector. Well, in order to find that vector, we just need to know what t is. Now we've solved for t. And so we can say that the force on the block by the cable, plug the 196.2 in there, is equal to 0, 196.2 newtons. Or this means it's in the positive y direction, so it's a force up with a magnitude of 196.2. Any questions about that? Okay. There are 3 specific cases that you need to be ready for this kind of stuff. And all of these are ones where there's nothing kind of keeping you from thinking your way through it, given what we've already talked about. But there are some sort of easier ways to go about it in these specific cases. So let me list out the 3 cases that we're going to see. So specific cases for Newton's second law. The first one is collections of bodies in contact, and this first one, we're going to be dealing with cases where all of these bodies have the same motion. So all of them are going to have the same acceleration. An example of this would be like a bunch of carts in a line with each other, and you push on the back one and it makes them all move as a single unit. Same acceleration. The second case is objects that are rolling or sliding on inclines. So we did a free body diagram of something like this somewhere. Well, this is an example of that. Both of these 2 bodies are on inclines. And so we're going to have sort of a special approach for that. So this is bodies that are rolling or sliding on inclines. And then the third one is collections of bodies connected by cables and pulleys. And the reason that this is different from that first category is that the accelerations of these bodies are going to be related, but they're going to be different. Okay, so this has different accelerations. Okay, so I'm going to start out with collections of bodies that have the same acceleration. And an example of this would be like, we've done free body diagrams of stuff like this before. Let's say we have these two rolling carts and they're pushing on each other, and there's a force of 50 newtons going this way. And we want to calculate something about the forces or something about the accelerations. So this is an example. And so the approach that we're going to use here is, first, our chosen body is going to be the whole collection treated as a single thing. So the chosen body is the entire collection of bodies. And you're going to use this to calculate the acceleration vector. Okay, and the benefit of this is once you calculate the acceleration for the whole system, that's the acceleration you can use for the individual bodies too. So now step 2 is, now that you know the acceleration, isolate the individual bodies, or the chosen body is an individual body. Okay, so let me go through the calculation with this example I drew up here. So we have a 5 kilogram cart on the left, and a 10 on the right. And then we have a 50 Newton force pushing this way. And let's say what we want to calculate is the force on the 5 kilogram cart by the 10 kilogram cart. Okay? Well, the first step is we're going to isolate the whole system as a single thing. So the outline of the free body looks something like this. There's a weight force acting down that's equal to the entire mass times 9.81. So 15 times 9.81 is 147.15. And then go around the boundary looking for contact. There's a pushing force from the ground. I'll call that N total. And then there's the 50 Newton force over here. Is this system free to move along the x-axis or the y-axis? X, yep. So the acceleration vector we're going to call A0. And now Newton's second law says negative 50, 0, plus 0 n total, plus 0, negative 147.15, is equal to the mass of what we've isolated, so that's 15, times the acceleration vector as we know it, which is A0. The x equation here says negative 50 is equal to 15a. And so A is equal to negative 3.3 repeating meters per second squared. Well, the acceleration vector is this. We just didn't originally know what that A was. Now we can plug in that negative 3.3 repeating. And so the acceleration vector is negative 3.3 repeating 0. Okay, so now that's the main use of isolating the whole system together. Now we're going to isolate one of the individual carts, knowing that its acceleration is going to be this, okay? So we're trying to calculate a force on the 5, so let's isolate the 5. So I'll draw a free body diagram of the 5. And the forces are a weight force going down. So that's 5 times 9.81, 49.05 newtons. A pushing force up from the ground. I'll call that N5, bless you. And then the last thing is we're going around the boundary of the 5 looking for contact. There's the place where the 10 is touching it. That's a pushing force. So that's perpendicular to the surface, toward the chosen body, and I'll give that a variable name. We already know the acceleration vector of this, so I can go right to Newton's second law. And it says negative r0 plus 0, negative 49.05, plus 0, n5, that's all three of those forces, is equal to the mass of this chosen body, 5, times its acceleration vector, which is negative 3.3 repeating 0. The x equation says negative R is equal to 5 times negative 3.3 repeating. So negative 16.6 repeating. So R is equal to 16.6 repeating newtons. This is the force vector we want. We just had to figure out what the value of R was. So now we can plug this value into that vector, and we get that the force on the 5 by the 10 is equal to negative 16.6 repeating 0. Or another way you can write it is that's in the negative x direction, so it's going this way with a magnitude of 16.6 repeating. Okay, so you might look at this problem and think, okay, what's the force that the 10 is applying to the 5? And if you look at this, you might think, oh, well, it's probably just that 50, you know? But it doesn't quite work out that way. Some of that force is kind of dissipated by the mass of the 10 kilogram. And so there's only 16.6 newtons that are applied to the 5 by the contact. Any questions about that? Okay. I'm not going to give you any homework since we have a test on Wednesday. And then I'll give you an assignment on this stuff after Wednesday.